Hello viewers, so far we have discussed the methods which can be used to calculate the real roots of nonlinear equations in one variable. These methods cannot be used to calculate complex roots. There are certain methods which can be used to calculate complex roots as well, and here we will discuss one of such methods. This method is called the Baristow's method, and it is capable of calculating real as well as complex roots. The method is based on factorization of the given polynomial equation. Remember that this method can be used only for polynomial equations. So, what we do? We factorize the polynomial equation. One factor will be a quadratic factor and the other factor will be the quotient of the division. In general form, if you have a polynomial of degree n, we can factorize this polynomial. One factor will be a quadratic factor which is of the form x square minus r x minus s, as you can see on your screen, and the other factor will be a polynomial of degree n minus 2. Here we give one example. Suppose we have a polynomial of degree 5. You can see on your screen equation 1. We factorize this polynomial with a quadratic factor which is x square minus 5x plus 3, and the remaining part is a polynomial of degree 3. The quadratic factor x square minus 5x plus 3 can be used to calculate the roots by using this standard formula. For quadratic factor x square minus r x minus s, the standard formula for roots is given in equation 3, where the roots are r plus minus under root r square plus 4s divided by 2. So, if you use this formula for the quadratic factor in equation 2, you will get the roots, the two roots which are 5 plus minus under root 13 divided by 2. So, we can generalize this method for a polynomial of degree n. The general form of the polynomial of degree n is given on your screen in equation 4, and suppose we have a quadratic factor x square minus r x minus s of this polynomial equation. So, if you divide this polynomial equation by this quadratic factor, you will get a quotient which is a polynomial of degree n minus 2 and a remainder term which is of the form of c x plus t. The quotient which is a polynomial of degree n minus 2 can be represented again in general form. As you can see in equation 5, the polynomial is represented with coefficients b, bn minus bn, bn minus 1, etc., and the quadratic factor is of course x square minus r x minus s. Since we do not know the quadratic factor at this point, we take some trial quadratic factor. That means, this quadratic factor will not divide the polynomial exactly, but there will be remainder term also. So, the polynomial with a trial quadratic factor x square minus r x minus x, the quotient given by equation 5 and a remainder term is given in equation 6. Equation 6 is equivalent to equation 4, that means, it is representing the original polynomial in factorized form with the remainder term also. Now, by multiplying the quadratic factor with the quotient polynomial and adding the remainder term, we can compare the coefficients of powers of x one by one, and we can get a relation between the coefficients in the two forms. The b coefficients are now related to the coefficients of original polynomial with coefficients a n. You can see that only the first coefficient of the quotient polynomial p n is constant, which is equal to a n, and all other coefficients will depend on the coefficient of quadratic factor r and s. They are function of r and s. They are not constant, but will depend on r and s. So, equation 7 gives you the relation between the coefficients. Now, if we want the quadratic factor to divide the original polynomial with no remainder term, that means the quadratic factor divides the polynomial completely, means it is a factor of the polynomial, then what we should do? We should reduce the remainder term to 0. So, our next aim is to reduce the remainder term to 0. That means, if we can do, rather we can adjust the coefficients r and s, so that the remainder terms becomes 0, for which both b 1 and b 0 should reduce to 0 by adjusting the coefficients r and s. To do this with the trial r and s values, suppose we have a correction term delta r in r and delta s in s. If we use the value r as r plus delta r and s as s plus delta s, suppose both b 1 and b 0, that is given in equation 8. So, we can use Taylor series expansion for equation 8 to find approximate value of the correction terms. So, you can see the expansion of b 1 and b 0, which are function of r and s, in equation 9 and 10. Again we say that if the correction terms delta r and delta r s are small, the powers of delta r and delta s higher than 2 and higher are neglected. So, neglecting the powers of delta r, 2 and higher powers, what we get? We get simplified equations which are given on your screen in equation 11 and 12. Now, these two equations can be used to solve for delta r and delta s. That means, we can use the Gauss elimination method to find the value of delta r and delta s. These two equations are representing simultaneous equation in variable delta r and delta s. b 1 and b 0 are of course constant, and delta b 1 upon delta r, delta b 1 upon delta s, these are coefficients of the variables delta r and delta s. So, using Gauss elimination method, we can find the value of delta r and delta s. These values are given in equation 13. You can see these values, the correction values are given delta r and delta s by using Gauss elimination method. There is another form which is you can find it in many books, and this is the determinant form, and these are equivalent to the equation 13, and we can write, or rather we can represent the correction terms in form of determinants. The stopping criteria of this method is again the absolute error. We will calculate the absolute error, that means, we calculate the correction term delta r and delta s, and if this becomes less than the allowed error, then we will say that the method has converges, and the quadratic factor will nearly divide the polynomial, and the roots of quadratic factor can be used as roots of the polynomial. Now, our problem is to calculate b 1 and b 0 and reduce them to 0. For this, what we do? We use the expressions in equation 13, and there you can see that b 1 and b 0 are related to other coefficients. You can see in equation 7 that this work is not so simple as it appears. You need to calculate b 1 and b 0, for that you need b 2 and b 3, for that you need b 4 and b 5, for that you need b 6 and b 7. Continuously you need to move upward, and you need to go up to a n and b n. So, we need to use equation 7 recursively to find the value of b 1 and b 0. Similarly, in the expression for delta r and delta s, you can see the derivatives of b 1 and b 0. The derivatives of b 1 and b 0 can be obtained by using equation 7, and these are given on your screen. In equation 15, we have write the derivatives of b 1 and b 0 with respect to r and s. Here again you can see that the derivative of b 1 with respect to r will need the derivative of b 2 and b 3. The derivative of b 2 will need the derivatives of b 3 and b 4, and so on. So, you have to move upward to the nth order. So, we can see that to To calculate delta B1 by delta R and delta B1 by delta S, we need to move upward and we need to find out all the derivatives of the higher order coefficients. We observe from these equations that we need to develop a relation between the coefficient starting from the first coefficient, that means nth coefficient, and move downward so that we can calculate the coefficient derivative of coefficient B1 and B0. So, we start from the first coefficient, that is Bn, which is equal to An, and since An is constant, we find the derivative of Bn with respect to R and S, and since An is constant, it will give us 0. So, we get the derivative of Bn, which is 0, and we name it by a new coefficient, that is say C, and we say that this is Cn. So, derivatives are represented by a new coefficient which we call Cn. Similarly, we get the derivative of Bn minus 1, and this will be equal to An. After some simplification, you will see that this is An, and we term it as Cn minus 1. We continue with the derivatives, and we find that the Bn minus 2 will depend on R and S, and it will depend on Cn and Cn minus 1 also, and we call it Cn minus 2. The derivative of Bn minus 3 will depend on R and S, and will also depend on Cn minus 1 and Cn minus 2, and we term it as Cn minus 3. Continuing in this way, we can generalize this relation, and we write the derivative of ith coefficient in B, and that is delta Bi by delta R, and this is related to the coefficient Ci plus 2, Ci plus 1, and we term it as Ci. We can find the derivative of coefficient B1 and B0, and we term them as C1 and C0. So, you can see that there is a continuous relation between the coefficient starting from the coefficient of nth order and going down to the coefficient of 0th order. The relation is a recurrence relation type, and we can use this recurrence relation to evaluate the coefficient C0 and C1. So, you can see on your screen how the coefficient C's are related to each other. Starting from Cn is equal to 0, we go continue with the C coefficients in downward direction, Cn minus 1, Cn minus 2, Cn minus 3, and so on, and the generalized relation for coefficient C, that is Ci is equal to S Ci plus 2 plus R Ci plus 1 plus Bi plus 1, and finally, we get the coefficient C1 and C0. We can find the derivative of B1 and B0 with respect to S, similar to the derivative with respect to R. The only thing is there is a slight change in the index, there is slight shifting in the index, and here we will give a brief account of it. In equation 21, you can see that the first derivative, that means delta Bn upon delta S is equal to Cn, and that is 0. The second derivative in this case is also 0, because there is no S term in the Bn minus 1 expression. So, we again get 0, that means delta Bn upon delta S is also equal to Cn. The all other terms are exactly same as we do for the derivative of B's with respect to R. Here the shifting is only of the index, and we shift the index of Cn by 1 in upward direction. So, we get the derivatives of Bn minus 1, Bn minus 2, Bn minus 3 with respect to S, and we name them Cn minus 1, Cn minus 2, and so on. Finally, we get the derivatives of B1 and B0 with respect to S, and we find that these are C2 and C1 in place of C1 and C0, which is given in equation 23. Using these coefficients, so finally, starting from Cn, we come down to C0, and using the last three coefficients C0, C1 and C2, we can obtain the correction term delta R and delta S as given in equation 24. So, this whole complex mathematical procedure can be followed to get the correction terms in delta R and delta S. Using these correction terms, we get the new value of R and S. R will be R plus delta R and S will be S plus delta S, and we will calculate the error in the iteration, and that will be equal to the sum of the two correction terms. If this error is greater than the allowed error, we repeat the whole procedure. So, with this mathematical analysis, we can write the solution procedure, rather it is not algorithm, but a solution procedure for the method. And the solution procedure you can see on your screen. We will start with the step 1, where we will read the degree of the polynomial, say n, and the allowed error epsilon, and we will then use a loop to read the coefficients of the polynomial, and then we will take the initial value of r and s, which are usually taken as 0 0. Then we again use a loop to calculate the coefficients bi of the quiescent polynomial by using equation 7. By using the coefficients bi, we again use a loop to calculate the coefficient ci by using equation 20. Then using equation 24, we calculate the correction term delta r and delta s. Then we calculate the error, sum of the absolute value of delta r and delta s. Then we compare this error with epsilon. If the error is greater than epsilon, then we go to step 4 and we restart the whole procedure. If the error becomes less than epsilon, we say that r and s are the coefficients of the quadratic factor, and we can solve the quadratic equation to get the roots of the polynomial. We print the root and stop. So, this is the solution procedure. Here we have some remarks about the Baristow's method. The method can be used only for polynomial equations. The quadratic factor of the polynomial is obtained by using the numerical procedure. That means, it is approximate quadratic factor, it is not exact quadratic factor. The roots of the quadratic factor are also roots of the polynomial. The roots may be real as well as complex, because this will depend on the value of r and s. So far we have discussed the methods for solving nonlinear equation in one variable. In many cases, we find a system of nonlinear equations in more than one variable, in several variables, and we will try to find out some numerical methods which can be used to find solution of the system of nonlinear equations in many variables. So, if you have n variables, you will need n nonlinear equations to get a solution. That means, you need a system of n nonlinear equations to find the solution for the n unknowns. However, to simplify, or rather to demonstrate the method, we will restrict ourselves only for the nonlinear equations in two variables. We can use some of the methods we have discussed earlier to find the solution of nonlinear equations in many variables. Here we will use Newton's, or rather Newton-Raphson method for finding solution of system of nonlinear equation in two variables. So, the general form of the nonlinear equations in two variables is given by equation 1, where we have two functions which are function of x, and both are function of x and y, function f1 and f2. Now, suppose as usually do in numerical method, suppose the initial guess is x0 and y0 for the two equations, and the exact root is suppose x is equal to a and y is equal to b. So, what we have? We have a correction term for both x0 and y0, and let the correction terms are h and k. For x we have the correction term h, and for y we have correction term k, and if we add h in x0, suppose we get a, and if we add k in y0, suppose we get b. So, if we take x 0 plus h and y 0 plus k in the function f1 and f2, the corresponding functions will be 0, because they will satisfy the function equations. A and b are exact roots, so they will satisfy the function equations. You can see in equation 2, this is what we are doing. We are substituting a by x 0 plus h and b by y 0 plus k in the function equations. So, we are getting these two simultaneous equations in two variables, and as an approximation for h and k to be small, we can expand equation 2 using Taylor series expansion around x 0 and y 0. So, you can see the Taylor series expansion of function f 1 in equation 3, and similarly we can get the expansion of function f 2 in equation 4. Now, the correction term h and k are small, therefore, we can neglect the terms of order h square and higher. Similarly, we can neglect the terms of order k square and higher, and we get the simplified form or rather approximate form of equation 3 and 4 as equation 5 and 6. The equation 5 and 6 are the simultaneous equations in h and k, where f 1 and f 2 are constants and delta f 1 by delta x and delta f 2 by delta x etcetera, these are the coefficients of h and k. So, again we can use the Gauss elimination method to solve these two simultaneous equations for the variables h and k. So, if we use the Gauss elimination method, the solution for the equations are given by h and k in equation 7 and 8. In 7 we have the expression for h, and in equation 8 we have the expression for k. Now, using these correction terms, we can find the next approximate root, and that will be x 1 and y 1. We will again use the same criteria for stopping the iteration, and that is we will calculate the error in the iteration, and that will be the sum of the errors in the two variables, that means in x and y, that will be absolute value of h and k. If this error is greater than epsilon, we will repeat the whole procedure, and if this error becomes less than epsilon, we will stop the procedure and write the roots as x 0 and y 0. The solution procedure is similar to the Newton-Raphson method, because this is extension of Newton-Raphson method for simultaneous equations. So, what we do, we just have two nonlinear equations in two variables, and we just have two approximate values x 0 and y 0 and start the procedure. So, the solution procedure is given on your screen. In step 1, we read the value of x 0 and y 0, we read of course the allowed error epsilon, then we calculate the function f 1 f 2 and the coefficients, that is delta f 1 by delta x and all these things at x 0 y 0. Then we use equation 7 and 8 to calculate the correction term h and k. Using these correction terms h and k, we calculate the next approximate value of x and y, that is x 1 and y 1 by using equation 9. Then we calculate the error in the iteration, and that is absolute value of h plus absolute value of k, and if this error is greater than epsilon, then we reinitialize the newly calculated value by the initial approximate values x 0 is equal to x 1, y 0 is equal to y 1, and then we go to step 2 and repeat the whole procedure. If the error becomes less than epsilon, then we stop the iterative procedure and write the roots at x 0 and y 0, and this is how we will be able to solve the set of simultaneous or the system of simultaneous equations. In today's lecture, we discussed the Best-Stokes method to find roots of polynomial equation. In Best-Stokes method, we obtain a quadratic factor of the polynomial, and the quadratic factor can be solved to give the roots which may be real or complex. So, this is the generalized method which gives us real or complex roots of the given polynomial equation. Remember that Best-Stokes method can be used only for polynomial equations. We also discussed the solution of system of nonlinear equation in several variables, and there we extended the Newton-Raphson method for solving a set of equations in two variables, and we just described the method and detailed the solution procedure. Hope you enjoyed the lecture. Thank you.